Can you please explain why RISE is so exciting?
Well, I can talk a little bit about how we perform the RISE experiment, for example, and what kind of information we can get from RISE. First of all, the RISE experiment is not done with a separate instrument. It's done with the actual radio system of the spacecraft together with the radio system on the Earth, which is our deep space network, the big dishes that you see, in the desert of California and Spain and Australia. And so the way the experiment is done is that there's a signal, a radio signal that's sent from the deep space network to the InSight's spacecraft at Mars. And the InSight's spacecraft in their radio system has something called a transponder, which both receives that signal and then immediately turns it around and sends it back to the Earth. And it does this so quickly and efficiently that it doesn't even break the shape of the wave, the radio wave, which is oscillating at hundreds of thousands of millions of times per second, gigahertz. But it turns it right around and sends it back. We know the small tiny delay inside the radio itself, and then it transmits it all the way back to Earth, where it's picked up again by the big dishes in the desert. And the Doppler shift of the frequencies in that signal plus the timing is used by the scientists and engineers on Earth to determine the location of InSight in space to within a very small amount, like less than a foot or 15 or 20 centimeters, and that's really incredible. I mean, this spacecraft is 60 or 100 million miles away from the Earth, and yet we can still figure out where it is that closely. And that precision allows us to watch the spacecraft during the day. We track it for about 1 hour per day, and during that hour, as the planet rotates, it makes a little bit of an arc, a little bit of a piece of a circle, and we can take that piece of a circle and figure out exactly where the North Pole of Mars is pointing. And just from that rotation, and the North Pole or the rotational pole actually moves, and it moves on a couple of different time scales. It has one time scale, it takes it about 160,000 years to kind of wobble around the same way that a top wobbles. And the speed of that wobble is related to how much of the mass, how much of the density of the planet is concentrated towards the center of the planet. So it's like an ice skater, and as they pull their arms in, they spin faster and faster because they are bringing the mass in closer to the center, and it conserves something that a physicist would call a moment of inertia. And so it spins faster and faster, and so and that also affects not just the speed of the spin, but the speed of the wobble, the top kind of a wobble. And that is, of course, very, very slow because, in 160,000 years, we don't really have that much time to sit around and wait for it, but we can measure a little bit of motion, not during the InSight mission, but we actually measured where the North Pole of Mars was pointing back during the Viking mission back in 1976, 77. And we measured it again during the Pathfinder mission, which was in 1996 and 1997, and it moved just a little bit, and we were able to measure that. But now InSight is about a little bit more than 20 years later, and so it has moved just a little bit more, and of course our technology is advanced. We can actually measure it a little bit more precisely now than we could in the 90s, and they could measure it a little bit better in the 90s than they could in the 1970s, so we'll get a much better measure of this small amount of motion, which tells us about how much of the mass is in the center of the planet. Now, that still doesn't tell us quite what the size of the core is, or the density of the core, the weight of the core, because those two things together go into the moment of inertia. So there's a trade-off. It can be a little bit bigger and a little bit lighter, or smaller and heavier. So we would like to be able to get those two things separately. And the way we do that is kind of interesting because not only does it go around very slowly, but it actually wobbles a little bit during the year. So, sometimes it has a wobble that's twice a year, another wobble that's 3 times a year, and these are called kind of resonances. But the size of those wobbles and the actual speed of the wobbles is related to the size, again, the size and the density of the core. And it's actually from the core kind of sloshing around inside, inside the planet, makes the planet kind of wobble a little bit around. And by watching that wobble during the course of the year, since we're looking at it every single day, and that wobble's not very much, we're talking about, just a few meters, maybe 10 meters of change in the direction of the North Pole of Mars. That wobble tells us, again, more information about the size and the density of the core. And we take those two things together, the speed of the very slow wobble and the speed and the size of that smaller, faster wobble, those two things together gives a very, very good measurement of the properties of the core, which is a really tough thing to do because that core is more than 1,000 kilometers, almost 2,000 kilometers below the surface of Mars. So this is one of the really important measurements that the InSight mission is going to accomplish.